This is Unit 7, Part 3. The control of blood pressure, the pressure within the blood vessels, is one of the major parameters that are under regulation or control, and there are both short-term controls and long-term control mechanisms. The short-term control systems include the nervous system. So the central nervous system does have an effect on on blood pressure, and also blood-borne chemical compounds that are released that have an effect. These short-term controls counteract moment-to-moment fluctuations in blood pressure that occur, and they do that by changing peripheral resistance, typically by causing either vasoconstriction, narrowing of the blood vessels in general, systemically, or in a local area, locally, or by vasodilation, either systemically throughout or locally in one particular area of the body. The short-term neural controls, controlled by the nervous system of the peripheral resistance, can therefore alter distribution of the blood in response to specific needs or demands of the body and the different areas of the body. I remind you the most important measure of the ability of the vascular system to perfuse and deliver blood to an area is the mean arterial pressure, and the mean arterial pressure is equal to the diastolic pressure plus 1/3 of the pulse pressure. And I remind you that the pulse pressure is the difference between the systolic and diastolic pressures. So the mean arterial pressure is maintained at a certain level by changes or alterations in the blood vessel diameter, either by vasodilation or vasoconstriction. And all of the nervous control mechanisms operate via reflex arcs. So that a reflex arc involves, it involves essentially how the entire nervous system, to describe it very generally, this is how the entire nervous system works, which is by collecting sensory information from the body, and of course from outside the body, but here we're talking inside the body. So it's collecting sensory information, and the kind of sensory information that's important for control of blood pressure is coming in through baroreceptors. Baroreceptors are pressure receptors. These are sensory nerves that can respond to the blood pressure level, and they send those signals into the central nervous system. And within the medulla, which is in the brain stem, you have centers that can respond to those signals coming in and send out an appropriate response, and they send them out via vasomotor fibers. So the vasomotor fibers in the medulla, the brain that part of the brain stem called the medulla, it's actually the medulla oblongata, will send out a signal, an appropriate signal, in response to the sensory information it's receiving. So it's a question of sensory information coming in, being processed, and then commands being sent out. And the processing is done in the vasomotors of centers. Vasomotor means muscle, motor referring to muscle, and vaso referring to blood vessels. So the muscle blood vessel centers in the brainstem, the medulla of the brainstem, will send out signals to through vasomotor nerve fibers to smooth muscle in the blood vessel walls. in a particular area or throughout the systemic circulation. It varies. Sometimes it's localized to a particular area of the body. Just to give you an example, if you've eaten a meal and you're digesting the meal, you're relaxed and you're digesting the meal, then there will be an increase in blood flow into the blood vessels that supply the small intestine or the intestines in general. And that's so that more blood can flow into there and take up the nutrients that are being absorbed and shunt them into the liver. So more blood will flow into that area, and the reason more blood flows into that area is because the smooth muscle in the blood vessels that feed blood to that region of the body will relax, so you get vasodilation and more blood flow in. So that's an example of overall of a region, particular localized region of the body, getting a command that changes the perfusion. Sometimes it can be the entire systemic circulation that gets a signal to cause some vasodilation or vasoconstriction. So it varies. In this situation, it's a reflex because, first of all, you're talking about involuntary, not consciously controlled tissue, involuntary smooth muscle. And also it's an immediate response. The sensory information comes in picked up from baroreceptors and sent into the central nervous system to the vasomotor centers in the brainstem and the medulla of the brainstem, and then a command is sent out via vasomotor fibers to either relax or constrict. So with relaxation you get vasodilation, with constriction you get vasoconstriction, or contraction. So vasoconstriction or vaso is because of contraction of the smooth muscle. So those are immediate. That's an immediate type of short-term mechanism that's mediated by neural controls to affect the peripheral resistance. Remember, the resistance is to flow is greatly affected by the diameter of the vessels. Resistance is equal to 1 over the radius to the 4th power. The smaller the radius, the higher the resistance. The larger the radius, the smaller the resistance. These vasomotor centers, as I said, are in the medulla of the brainstem, and they control blood vessel diameter because they can send out signals to the smooth muscle around the blood vessels. They maintain a certain tone and by tone I mean a certain level of contraction of those muscles. They're always somewhat contracted, because if a muscle is somewhat partially contracted, then it can either contract further, causing vasoconstriction, or relax, causing vasodilation. If you're fully relaxed, you cannot all the time, then you can't vasodilate from that position, right? So they maintain a certain tone, and the tone refers to the level of contraction of the muscle by, sending signals to the smooth muscle of the blood vessels, particularly the arterioles. The arterioles have the area of the vasculature on the arterial side that has the greatest effect. I remind you, you also have cardiovascular, you also had cardiac centers, and so the vasomotor center plus the cardiac center together form the cardiovascular center. Okay, there were cardiac centers in the medulla, and there are also vasomotor centers. Cardiac centers affect the cardiac muscle in the heart, and the vasomotor centers affect the smooth muscle in different areas of the blood vessel, the blood vasculature. And they together can control blood pressure by controlling or changing cardiac output, and which is done by the cardiac centers, and blood vessel diameter, which is done by the vasomotor centers. The tissue in the blood vessels, the muscle tissue, is involuntary. Therefore, as I've explained to you in the past, in all the involuntary responses or tissues are controlled by the part of the central nervous system that's called the autonomic nervous system. And there are two divisions to the autonomic nervous system. There is the sympathetic division, and there is the parasympathetic division. I'm just going to write para, but it's parasympathetic. Two divisions of the autonomic nervous system, and these have differing effects on whatever tissue we're looking at, whatever particular tissue you're looking at. There are, in fact, two major groupings of tissue that are controlled by the autonomic nervous system: muscle, involuntary muscle, that includes cardiac muscle and smooth muscle, and gland tissue. If sympathetic output is increased from the vasomotor center, then that will result in vasoconstriction and a rise in blood pressure. If it is decreased, then you'll get vasodilation and blood pressure drops. Okay. The activity of that part of the central nervous system that controls the smooth muscle around blood vessels, the vasomotor center, can be modified by signals received from baroreceptors, which are essentially pressure receptors, and chemoreceptors that are sensitive and responsive to three things: oxygen level, carbon dioxide level, and the level of hydrogen ions. I remind you, because you should know this, that the concentration, so when you see something in square brackets like that, it means the concentration, so that the concentration of hydrogen ions, in fact, is what controls or determines pH levels. The higher the concentration of hydrogen ions, the lower the pH level, and things are therefore more acid. And the lower the high hydrogen ion concentrations, the higher the pH, things are more alkaline. So depending upon O2 levels, PO2 in fact, and CO2 levels, PCO2, the partial pressure of oxygen, the partial pressure of CO2, and the hydrogen ion concentrations, in other words the pH, these chemoreceptors can respond and send signals that will change vasomotor activity. Okay. Also, your own higher brain centers can have an effect, so that if you are, for example, under certain degrees of stress, then that can have not direct but indirect have an indirect effect on vasomotor activity. There are certain chemical compounds that can be released into the blood that can also affect this vasomotor activity, and hormones. I would say that one of the key hormones that affects vasomotor activity would be thyroxine, produced by the thyroid gland. And although it is a neurotransmitter released at the ends of sympathetic blood nerves. It is also a hormone released from the adrenal glands, not thyroxine. Thyroxine is produced by the thyroid gland. But another one would be adrenaline or adrenaline or epinephrine. Let's put epinephrine, but you can put adrenaline, which also is released from the adrenal glands into the bloodstream, and therefore is also a hormone, but it essentially has neurotransmitter effects, epinephrine. Okay, there we go. So all of these things can affect the level or degree of activity output of the vasomotor centers, baroreceptor, chemoreceptors for O2, CO2, and pH or hydrogen ions, higher brain centers, not the brain stem, but higher up, bloodborne chemical compounds, and hormones. Okay, let's look at a situation where that involves short-term control mechanisms of blood pressure, involving signals that come in from the pressure receptors or baroreceptors that trigger a reflex activity. And in this case, it's a it's a change in blood pressure, and it's an increase. So in the example here, the baroreceptors are starting a reflex, and the sensory signal, the initial sensory signal is increase in blood pressure or a high blood pressure, okay, an unusually high temporary rise in blood pressure. That's what the baroreceptors are being triggered by, and they send signals into what's called, again, the brainstem. And these centers in the brainstem are given different names, but essentially we're talking about cardiovascular centers. All right, they are present in that brainstem, and they will control both heart and blood vessel activity. So in this case, this particular center that gets stimulated in the brainstem is called the cardioinhibitory center, and it will send signals out along these vasomotor fibers, nerve fibers, right? So this is output from the central nervous system, so it's called motor output because it's going towards muscles, and it will cause vasodilation, an increase in blood vessel diameter, which is a generalized, widespread increase in vessel diameter, and a decrease in heart rate. Now that decrease in heart rate will trigger a drop in cardiac output, because cardiac output is equal to heart rate times stroke volume, right? And peripheral resistance will drop because of the increase in vessel diameter, which really is vasodilation. And with a drop in cardiac output and a drop in peripheral resistance, you get a drop in blood pressure. So the end effect is the drop in blood pressure. The whole thing was started by a short-term, sudden, a quick change in blood pressure, a higher than normal increased blood pressure, and the end effect is a decrease in blood pressure. So the body is responding to, it's a feedback mechanism, right? Or signals come in, they get processed in this cardioinhibitory center, you get an output which causes vasodilation, relaxation of those muscles around the blood vessels, a decrease in heart rate. So you have cardiac output going down and peripheral resistance going down, and the end effect is a drop in blood pressure. And this kind of response occurs all the time. You know, as you go through your day and you have different experiences, and you have different activities and positioning of your body and muscle activity, you will have these short changes that require a shift, a response. It's constantly happening. Okay, let's go to a different one. In this case, the change in the situation and the sensory input, the signals coming in from baroreceptors are that, the baroreceptor initiated. In this case, the signal coming in is a drop in blood pressure. Okay, that's the sensory input, goes into the brain, into the central nervous system, and is detected in the cardiovascular center, the specific part of the cardiovascular center, which is called the cardioacceleratory center. The response from there is the overall response is causes an increase in cardiac output and an increase in peripheral resistance, and that happens because you get vasoconstriction and increased heart rate. It's actually not shown here. I should have had it here. So the response, immediate direct effect is an increase in heart rate. Okay, which causes the increase in cardiac output, and an increase in peripheral resistance due to vasoconstriction, which both of which end up causing the end effect. So it's a cause and effect relationship, right? The end effect is, and this, by the way, is an R. I didn't draw it very well. So the end effect is an increase in blood pressure. And that's the proper, appropriate response, because the whole thing started with a decline, a drop in blood pressure. An example of something like that would be you're lying in bed and you have and you're lying, horizontally lying on your bed, and you've been lying there for 8 hours or 10 hours with some people, and the alarm goes off and you suddenly jump out of your bed. Okay, now if you jump from a lying position to a vertical position, your heart has not been pumping hard enough to deliver blood up against gravity, and you can get a sudden drop in blood pressure leading up to the brain, and you could get dizzy. Some people even faint. And many of you may have experienced this. You jump out of the bed after having been there for a long time and vertical, and you get dizzy because your blood pressure drops. Well, the response is that, that drop in blood pressure is detected, sent into the cardioacceleratory center. The immediate response, these are short-term mechanism response, the immediate response is that the heart rate rises, and you get a increased contraction of the smooth muscle around the blood vessel, causing an increased peripheral resistance, which also adds to higher blood pressure. The heart rate increasing causes higher cardiac output, so you have an increase in cardiac output that adds to blood pressure. Some increased peripheral resistance also increases blood pressure, so blood shoots up with more pressure up towards the brain. That increased blood pressure returns things to where they should be. And this kind of thing is shown, what I've just been describing to you is shown, and you can go through this on, on your own. All of these things are shown here. On this side, it's the stimulus is a rise in blood pressure, so blood pressure is higher. And then these responses here occur to bring it back to its normal level. And here, in the example, and what's described is a drop in blood pressure, and these responses occur, bringing it back to, again, the normal level. All right, so I would recommend you go through this. Okay, let's move on to another type of short-term mechanism that can control blood pressure. These are chemical molecules that can be chemical controls. Well, this is a response to actually, I don't know if chemical controls is the right word. I would, think of this just like the previous one we talked about, baroreceptor initiated reflexes. I would call this chemoreceptor initiated reflexes, because it's the chemoreceptors in this case that pick up changes and send that sensory information into the central nervous system to initiate responses. So chemoreceptor initiated responses or reflexes. The previous was baroreceptor initiated. It's a little difficult writing with the initiated reflexes. So as I told you before, you do have reflexes, changes in levels of the PO2 and the PCO2 in the body, in the blood. And these can be picked up by what are called chemoreceptors. And those signals can be sent into the central nervous system and trigger responses, reflex responses. The chemoreceptors, the key chemoreceptors, are found in the carotid arteries on either side of the neck. In those large arteries on either side of the neck, they are called carotid bodies. And also in the aortic arch, you have what's called the aortic body. So you have carotid bodies in the either side, in the carotid arteries on either side of your neck, which sense blood pressure of the blood going up to the brain, one of the most pressure sensitive organs. And you also have aortic chemoreceptors that sense changes in the blood, not blood pressure. I'm sorry, I said blood pressure before. Chemoreceptors in the carotid arteries detecting changes in PO2 and PCO2 levels, and chemoreceptors also in the aortic bodies, which is in the aortic arch, that the aorta supplies the entire rest of the body. So these sensory information can send signals into the brain stem, the medulla in the brain stem, in the central nervous system. And those areas can affect the blood pressure, as you know. So sensory information from chemoreceptors in response to O2 and PCO2, PO2 and PCO2 will send signals into the brain stem and can result in responses that change blood pressure. Higher centers, and two parts of your brain that are important in that are the cortex and the hypothalamus, can also modify blood pressure. So, are there responses, chemical molecules that are released into the bloodstream that can have an effect on changing blood pressure. In this case, we'll first talk about increasing blood pressure. Chemical compounds that can increase blood pressure, yes. There are adrenal medullary hormones that can be released. The adrenal medullary hormones include norepinephrine and epinephrine, also called noradrenaline and adrenaline. And these, all hormones, by the way, are released in the bloodstream. These can increase blood pressure because they have an effect on increasing heart rate and heart contractility, therefore cardiac output, and also can cause vasoconstriction in the peripheral. Well, let's not get into that. They have an effect on cardiac output. There's also another hormone that ADH, antidiuretic hormone, that's released from another part of the body, ADH. It can cause intense vasoconstriction. If you get that, you get higher blood pressure. So if you have extremely low BP, it'll trigger ADH release that causes intense vasoconstriction, raising blood pressure in response. So this is low blood pressure triggers ADH release and will cause vasoconstriction. There's another molecule. It's not released by the kidney. In fact, it's a whole sequence of events, and you'll learn more about this when you do renal physiology in the second semester. Not this semester, but I'll mention it to you now. I wouldn't hold you responsible for knowing the pathway. But the kidney responds to lower than normal blood pressure by releasing a hormone called renin. And renin will act on a molecule in your blood plasma called angiotensin 1. And angiotensin 1, once activated with renin, activates angiotensin 1, then angiotensin 1 is converted into angiotensin 2, and angiotensin 2, again, like ADH, can trigger intense vasoconstriction, causing a rise in blood pressure. Right? Each of these things can cause a rise in blood pressure. These cause a rise in blood pressure. Norepinephrine and epinephrine, ADH, can cause a rise in blood pressure. Angiotensin 2 will cause a rise in blood pressure. And the last one is our chemical compounds that can be released from the endothelial cells that line the blood vasculature. Remember, the whole blood vasculature is paved by endothelial cells, and these can also cause vasoconstriction, typically acting quite locally. One is this one. Okay, I think I'll pause here. Okay. There are also chemical compounds that decrease blood pressure. Again, you'll hear more about some of these later in your program. And certainly this one is a product of the it's produced in the heart, in the atrial wall, and you'll hear more about it when you learn about different hormones, I guess. It's called atrial natriuretic peptide. It causes changes. Actually, it has an effect on the kidneys, but it will cause an increase output in urine and sodium. So it causes a drop in blood volume and blood pressure. Nitric oxide is a gas that can be dissolved in the plasma and has very potent vasodilation effects. There are also some inflammatory molecules that are released during inflammation, which cause vasodilation. Vasodilation always occurs in an area of inflammation. There's increased blood flow into the area. You have redness, swelling because of increased blood flow and increased fluid going into the tissues. All of these that I've mentioned till now are, and before with the compounds that increase blood pressure, all of them that I mentioned are natural compounds produced in the body. This one is not. Alcohol, it will cause a drop in blood pressure, and it acts by inhibiting antidiuretic hormone, ADH. Okay, let's talk about long-term mechanisms of blood pressure control. One of them is mediated by the kidneys. So it's a renal regulatory process. And this occurs by the fact that the kidneys can change the volume of the fluid of the blood. It can reduce the overall volume by putting out more water, or it can conserve water and retain it, and in this way have an effect on a long-term effect on blood pressure. So the kidneys can act by altering blood volume. If there's an increase in blood pressure, it will stimulate the kidneys to eliminate more water. So the kidneys filter the blood and more water goes out, and thus it reduces blood pressure, because with a drop in volume you get a drop in pressure in the blood vasculature. And if there is an overall decrease in blood pressure, then that will stimulate the kidneys to retain more water, not put out as much, thus increasing blood pressure. Unfortunately, these kind of signals that trigger the kidneys to do this will eventually become, if the blood pressure is chronically high, always consistently it's high for a long period of time, or low for a long period of time, then you stop getting responses. You get adaptation to that change condition, and they don't respond anymore, and the person gets chronic high or chronic low blood pressure that the kidneys don't regulate. The kidney action can be direct or indirect in the maintenance of overall long-term maintenance of blood pressure. A direct renal mechanism is altering blood volume that I just discussed by increasing output of fluid, increasing the urine outputs, that brings pressure down, or decreasing the urine output, that helps maintain pressure and even bring it up. Indirectly, the mechanism involves the renin-angiotensin mechanism that I described earlier, where you have a molecule called renin released from the kidneys in response to low blood pressure. And renin will act on, I'm not going to write it out, but I'll just put A for angiotensin. It'll act on angiotensin 1 to activate, well, it acts on angiotensinogen to form angiotensin 1, and then angiotensin 1 is converted to angiotensin 2. And there are a number of effects of angiotensin 2, including, we've already spoken about, it's a potent vasoconstrictor, which would raise blood pressure, but it has other effects, which I'll maybe discuss in a little while. Okay. Yeah, and here is some of it. So this is what I was describing, writing before. If the initial stimulus, if the condition changes so you have a drop in blood pressure, then the kidneys will respond to that by releasing this hormone called renin. And renin acts on a protein in the plasma called angiotensinogen. Whenever you see something that ends in OGEN, you should realize that it is an inactive form. This protein gets activated by renin to form angiotensin 1. And then angiotensin 1 is converted by, it's cut by an enzyme. It's converted to angiotensin 2. And the molecule that converts angiotensin 1 to angiotensin 2 is found in the lungs, and it's called angiotensin converting enzyme, or ACE, ACE. As I said, angiotensin 2 is a potent vasoconstrictor, which causes blood pressure increase. But it also has an effect on the adrenal glands to stimulate secretion or release of a hormone called aldosterone. And aldosterone has an effect on the kidneys of increasing reabsorption of sodium. So the fluids that the kidney filters out undergo a lot of reabsorption, and one of the things that can get reabsorbed more or less, depending upon needs, is sodium. And the kidneys, under the effect of aldosterone, will increase their reabsorption of sodium. And when you increase your sodium levels, you also increase, or reabsorption of sodium, you also always increase reabsorption of water, because where the sodium goes, the water will follow in the kidneys. The other thing it does is that it will, and of course if you have more sodium and more water, your blood pressure goes up. And the other thing is that it will stimulate antidiuretic hormone release, which also enhances water reabsorption. So drop in blood pressure, kidneys release renin, acting on angiotensinogen to form angiotensin 1. Angiotensin 1 is acted on by ACE to form angiotensin 2, and angiotensin 2 does the following things to increase blood pressure. It has vasoconstrictor activity on the smooth muscle and around the peripheral, around the systemic blood vessels. It stimulates aldosterone secretion from the adrenal glands. The adrenal glands sit on top of the kidneys. And aldosterone increases reabsorption of sodium and therefore water, and also stimulates ADH release. ADH is, in fact, I didn't mention it earlier, but ADH is a hormone produced in a gland in your brain called the pituitary gland. Okay, which again you'll learn more about when you do endocrinology in the second semester. So ADH is released by the pituitary gland when stimulated by aldosterone, and that enhances water reabsorption in the kidneys. Again, all of these lead to increased blood pressure. We were talking about the long-term regulatory mechanisms that act in response to a decrease in blood pressure, which is picked up by the baroreceptors. Remember, I told you the baroreceptors are present in the carotid arteries. They are called carotid bodies, and also the aorta, which is called the aortic body. And there, those baroreceptors or pressure receptors send sensory information up to the brainstem, which triggers strictly kidneys and blood pressure. And there, what you get is baroreceptors sending out responses that can directly trigger renin release from the kidney. And renin actually is released in two ways. One is through those sympathetic signals from the brainstem, but also direct response, the kidney responding to drop in blood pressure and releasing renin. And renin release will act on the protein in the blood plasma called angiotensinogen, which is converted by renin to angiotensin 1 and then converted to angiotensin 2 by ACE, which is in the lungs and stands for angiotensin converting enzyme. So you get angiotensin 2, which can directly has a direct vasoconstrictory action. So you get vasoconstriction, decreased diameter of the blood vessels systemically, and therefore an increase in the overall blood pressure, that was the point, to get this response in due to it needing to be raised from the abnormally decreased level. The other thing that angiotensin 2 does is it acts on the adrenal glands to trigger them to release aldosterone. And aldosterone has a couple effects. One is that it will increase sodium reabsorption in the kidneys. So you put out less sodium, you retain sodium, and when you retain sodium, you retain water. And both of these will cause an increase in the volume of blood that causes increase in blood pressure. Angiotensin 2 also has a third action, and that is that it will trigger antidiuretic or ADH release from the pituitary gland, which increases water resorption and again causes an increase in blood volume, therefore leading to increase in blood pressure. And lastly, overall, the drop in blood pressure does cause kidneys to to retain more of the water that they've. Kidney function involves first forming a filtrate fluid into the tubular system that leads to the outside, but then more of that gets reabsorbed or retained, so less filtrate is formed, helping maintain blood volume and therefore blood pressure. So that's just a review of the effects of decreased blood pressure and the response in the kidneys to increase it and the mechanisms leading to that. All of these flow charts are extremely useful as a way of thinking your way through the system and going through it and reviewing and giving you an idea of whether you do understand how these regulatory mechanisms work. This is really physiology. If you understand how things are structured, that's good. If you understand how they work, that's fine, but it's how they respond and regulate physiological systems levels that really tells you whether you understand it, if this makes sense to you. Okay, let's move on. We'll talk about other topics. Blood pressure is monitored. It's one of the vital signs that is regularly checked. The difference, of course, between a sign and a symptom is that a symptom is something that the person can actually feel and experience, but a sign like body temperature, blood pressure, respiration rate, things like that, those are things that need to be measured. These are the vital signs. One of them, blood pressure, is a vital sign. It includes pulse, BP, respiratory rate, and body temperature. The thing about monitoring blood pressure is that it involves taking the pulse and at the same time altering that pulse. The pulse, of course, is a pressure wave caused by the contraction of the heart sending out a pressure wave which causes bulging out or expansion of elastic arteries and then their recoil. So that pulse is the expansion and recoil of the elastic arteries, typically taken at the risk not the wrist, taken at the wrist from the radial artery at the wrist, and pulse will vary from moment to moment depending on your activity, body position, and overall health. The way that involves or is tied in directly with blood pressure is that you can use it to indirectly, you can use the pulse to indirectly measure blood pressure using a sphygmomanometer, blood pressure cuff. It's placed on the arm above the elbow, superior to the elbow, and the pressure in the cuff is increased until it's greater than the systolic blood pressure in the brachial artery that runs down the upper arm, middle of the upper arm. So by raising the pressure in the cuff higher than systolic, you actually cut off the flow of blood. So if you're listening with a stethoscope just below the pressure cuff on the upper arm, and you're listening just below that at the brachial artery, once you get above the systolic blood pressure, once you inflate the cuff above the systolic blood pressure, you will no longer hear any flow. You'll no longer hear the beating of the flow of blood. You've cut it off. Then you slowly deflate the cuff, and as soon as you hear a sound of the blood coming through, as soon as the blood starts coming through, you'll start hearing the sound of that flow. And that first sound, if you look at the pressure cuff, that'll be you've reduced the pressure, the inflation of the cuff enough that you've reached the systolic pressure, equivalent to the systolic pressure. And now the blood is starting to just sneak past and get through. As you decrease the pressure so that determines systolic pressure, and as you decrease the pressure further in the pressure cuff, eventually you'll stop hearing sound because there's no more blocking of the flow by the pressure cuff, and it's no longer turbulent flow. It runs smoothly and there's no more sound. So as soon as the sound disappears, that point is the diastolic pressure. And in that way you can indirectly use the pressure cuff and its effect on the pulse to determine blood pressure. There is significant cycling, overall general waves of change over a 24-hour period in the blood pressure, usually typically highest in the morning and then dropping off through the day, but there's also moment-to-moment change depending upon physical activity and body positioning, and there are a host of other factors that can have an effect overall on blood pressure. The status of having a low blood pressure overall, a systolic pressure below 100, is called hypotension. And if a person has a sustained elevated blood pressure of 140/90 or higher, then they have hypertension. Although I think now they're talking, I guess 85/90 is indicative of beginnings of hypertension. There are always transient elevations from normal. You can get spikes caused by physical exertion, emotional upset, although it has to be quite strong, fever, a lot of things can cause transient elevations, but overall chronic elevations, they're the things to watch out for. If you have a chronically elevated blood pressure, that's bad. It can be a major cause of heart failure, indicative of vascular disease. It can cause renal failure and stroke. Hypertension, there's different terms applied to hypertension, different types of hypertension. Orthostatic hypotension is a temporary low blood pressure that occurs when a person suddenly rises from a seated or horizontal reclining position. Their overall regulatory mechanisms don't respond quickly enough to increase the activity of the heart and the vascular system to drop in blood pressure, so they don't they don't get feedback and respond fast enough to that feedback, so that they have a temporary dizziness. With chronic, and that temporary dizziness is called orthostatic hypotension. However, chronic hypotension is quite different. It could indicate poor nutrition. Sometimes it's a warning sign of a endocrine disorder called Addison's disease, which I won't get into. Acute hypertension, very sudden acute hypertension, could be a sign of circulatory shock. It can threaten patients who are in the OR undergoing surgery. It can occur, or ICU. Sometimes with infection, they get a sudden low blood pressure. Their regulatory mechanisms can't respond properly, and they have much too low blood pressure, acute hypertension. High blood pressure or hypertension can also be transient or a chronic kind of persistent type of hypertension. It's typically divided into two types: primary hypertension and secondary hypertension. Primary is also called essential hypertension. The risk factors, in other words, factors or characteristics that tend to be associated or lead to primary high blood pressure, primary hypertension, include diet, obesity, age, etc. All of these can lead to primary hypertension. Secondary hypertension is when the blood pressure, the increased blood pressure, is not the direct problem, but is secondary to some other identifiable problem. So in a person who has excessive renin secretion, for example, because of the excess renin secretion, they may have hypertension, so it's secondary to that. People with arteriosclerosis, which comes often with aging, is also a cause of secondary hypertension, and some endocrine disorders. Now, blood flows through different tissues and is under different regulatory effects for different organs, depending upon the function of the organ. We're going to go through that, but first we'll talk about blood flow through tissues in general, which is really tissue perfusion, the perfusion of the tissue with blood. Now, that flow is there in order to deliver oxygen and nutrients and remove metabolic wastes, including carbon dioxide. It's also involved in the gas exchange in the lungs, absorption of nutrients from the digestive tract, and urine formation in the kidneys. You need good, proper flow through the kidneys at appropriate pressure to get urine formation. So it needs to be precisely, the flow of blood in different parts of the body needs to be precisely regulated to the right level in order to have the tissue that is moving through to function properly. The velocity or speed that the blood flows through changes as the blood flows through the system. It changes throughout the circulatory system. It is typically inversely proportional to the cross-sectional area. That's an important concept for you to understand, because it's not just the, if you look at the vasculature and you have a large artery feeding into smaller structures, multiple smaller structures, then it's not just the flow is not, the velocity of the flow is not just the diameter of each of these smaller blood vessels, but it's equal to the total cross-sectional area at each level here. So you have to take the sum of it. If the sum of it is in fact greater, if the diameter is greater, if it splits up enough so that it is greater in cross-sectional area than the vessel feeding into it, then the blood will slow down. So if you look at all of these different cross-sectional areas of all of these, if the sum total of that is greater than this, then the blood flow will be slower. The velocity will slow down. So it's inversely proportional to the total cross-sectional area. As the cross-sectional area goes up at that level, then it will, if it goes up, then the blood slows down, and if it gets narrower, the blood flow velocity will be higher. When you get to the capillary level, because there are so many in any one capillary bed, there are so many capillaries, it actually slows down tremendously, and in that way you have enough time to have adequate exchange between the blood and the tissue of gases and nutrients and etc. And so when we look at it, we always have to consider where we are in the circulation, right? Whether you're on the arterial side here or the venous side of the circulation or within the capillaries here. And you need to consider the total cross-sectional area as well. And when you look at it, you see that the sum total cross-sectional area in the larger aorta and arteries is fairly low, and you have a very high blood velocity there in these larger ones here. But once you get into the arterioles, especially here in these just before the capillaries, the total cross-sectional area rises up quite a bit. And as a result, the velocity drops down. And once you get into the capillaries, you're at the peak total cross-sectional area, because all the many capillaries in each capillary bed have, if you sum up their total cross-sectional area, it's quite large, so the velocity is low. And then it goes into the venules and veins, and eventually leading back to the heart, which is here, right? And the velocity does go up somewhat, but not that much. Now, most blood flow is automatically adjusted through a process called autoregulation, and it's adjusted in order to meet the appropriate needs of the tissue at any given time. It is controlled. The flow of blood is controlled within the organ itself by changes in the diameter of the local arterioles feeding the capillaries. Typically the mean arterial pressure overall in the systemic circulation remains constant, but changing local demands in any one given organ or tissue can be responded to, so that the amount of blood being delivered to that area is enough to meet the needs of that tissue at any given particular time. Okay, so yes, on average, overall, mean arterial pressure is constant, and yet you can have more blood flow into one area at a certain point in time because of certain requirements. For example, if you're outside in the cold, your mean arterial pressure will be maintained at a normal, constant, relatively constant level, but you will have more flow of blood. You'll have less flow of blood into your skin, so that you don't lose heat from that blood flow at the surface of your body, and blood is redirected to the rest of the body to conserve heat and maintain the appropriate core body temperature. There are typically, responses that are required for appropriate metabolism to occur. Metabolism, of course, is the overall biochemical reactions that need to occur in tissues. If you so a lot of autoregulation is response to that, to those needs, and declining tissue nutrition or oxygen levels will stimulate autoregulatory mechanisms that will provide typically increase in flow. The hemoglobin itself can deliver oxygen to tissues, but it also has the ability to deliver nitric oxide that can increase, that can help increase vasodilation so that more oxygen is provided to the tissues in that area. Other autoregulatory chemical compounds that can trigger autoregulatory responses include all of these. I wouldn't memorize them, but realize that the metabolic activity within the tissue has an effect on the blood flow into that tissue at any one time. There are regulatory mechanisms under control of muscle. So these are myogenic, meaning muscle generated or muscle created controls. If you have either inadequate perfusion or the perfusion is too high and your pressure is too high, then the response it will trigger an autoregulatory response. It triggers the myogenic response, stimulation of the vascular smooth muscle around the blood vessel. Vascular muscle will respond directly to an increase in vascular pressure with it'll trigger that increase in vascular pressure causes a stretching of the smooth muscle, and that will trigger an increase in the degree of contraction of the smooth muscle, so which is an increase in the tone. In other words, it causes vasoconstriction. When you stretch out smooth muscle, typically it responds by contracting, not all the way, but partially. So if you increase pressure and you stretch out the walls of the blood vessel, because of that increase in pressure, the smooth muscle is stretched and it contracts, so you'll get vasoconstriction. So that's an autoregulatory response. The other type of autoregulatory response to the vascular smooth muscle is a direct response to stretch. A direct response to the reduction in stretching. It will relax, causing vasodilation, which promotes increased flow. So if it's stretched too much by increased vascular pressure above the normal amount, it will constrict. The smooth muscle will contract, and you'll have vasoconstriction to reduce it. And if it's reduced if there's a reduction in the stretch of the blood vessel wall because the blood pressure is lower, then you'll get relaxation, vasodilation, which increases blood flow into the tissue. Okay. Autoregulation has long-term aspects or characteristics to it. When short-term autoregulation doesn't meet the tissue's nutrient requirements, you get long-term autoregulatory responses. This can take weeks or months to develop to increase the local blood flow. So if blood flow is not adequate and it cannot be regulated by short-term responses like vasodilation, then you'll get responses that develop to help increase the blood flow, but they can take a long time. One of those is the growth into that tissue of new blood vessels, and this is called angiogenesis. So new blood vessels will grow. The number of vessels to the region increases. The existing vessels can enlarge. If a blood vessel in the heart becomes partially blocked, you can get this is an example strictly in the heart, you can get development of a new vessel around that area. And typically when people are at high altitudes for a prolonged period of time, you'll also get an increase in growth of new blood vessels. So at high altitude, the PO2 is lower, so people get more blood vessels forming. That takes quite a while. You have to be there for a long time.
And that's the end of Unit 7, Part 3.